Hello, dear participants. Welcome. First of all, I would like to start by introducing myself. It's Ömer Miraç Kökçam, a research assistant and master student at Fırat University in Turkey, Department of Software Engineering. In my presentation today, I will share the results of our research titled Deep Learning Based Brain Tumor Classification for MR images using ResNet 50, which we conducted together with my professors Aytu Boyacı from Turkish National Defense University and Muhammed Emre Çolak from Fırat University. In this study, we tried to show how artificial intelligence and deep learning technologies can revolutionize the field of medical imaging. In particular, we used the ResNet 50 model pre-trained by Google research team to classify brain tumors on a dataset that has been little studied before. Let's start the introduction. Brain tumors are serious abnormalities that affect critical organs such as the brain and can significantly reduce the quality of life for patients. Classification of these tumors plays a major role in treatment planning, but unfortunately, manual classification processes are both time-consuming and require high expertise. Therefore, automated classification methods such as deep learning have great potential to improve accuracy and speed up the diagnostic process. We have conducted studies to evaluate this potential and demonstrate the role of artificial intelligence in the classification of brain tumors. Details about the datasets such as size, diversity of images, and annotation quality are critical for the model's performance. The dataset's quality directly impacts the model's ability to accurately classify brain tumors, emphasizing the importance of robust data collection. In our study, we used a dataset of brain MR images obtained from the Kaggle platform. The dataset contains four main classes: glioma, meningioma, tumor-free, and pituitary. Each category has characteristic image features that make it easy to distinguish between tumor types and tumor-free types. The training set contains 2,000 images from each category, and the test and validation sets contains 250 images from each category, totaling 10,000 images. Each sample with a resolution of 512 by 512 pixels. Before being integrated into the pre-trained ResNet 50 model, the dataset undergoes a basic pre-processing routine. First, all image data is systematically divided into three separate subsets: training, test, and validation. The training set accounts for 80% of the total, while the test and validation sets are equally distributed as 10% each. To reduce the computational load, the native resolution of the MR images is effectively reduced from 512 by 512 pixels to 224 by 224 pixels. This size reduction speeds up the network performance while maintaining the potential to achieve improved diagnostic results. After the size reduction, the training images are randomly mixed to ensure that the model encounters the dataset without any inherent bias. The final preprocessing step is the normalization of pixel values, which is done by scaling each pixel's RGB values to the range 0 to 1 by dividing by 255. This normalization normalizes the input features, optimizing the gradient descent optimization process in the neural network. In our study, we used the ResNet-50 architecture pre-trained with the ImageNet21K dataset. ResNet-50 is based on the residual learning framework, which is considered a milestone in deep learning. This model is known for its ability to model complex features and maintain its performance even over long training sequences. The ResNet-50 model is a deep neural network known for its skip connections, enabling the training of deeper networks and reducing the vanishing gradient problem that it is shown as in this picture. While training ResNet-50 adjusts its weights through backpropagation to classify brain tumor images, aiming for highly accurate predictions. In this picture, shows a visual representation of the adapted ResNet-50 architecture. In this study, we utilize a variety of performance metrics to evaluate our model, including confusion metrics, accuracy, precision, recall, specificity, and F1 score, as well as loss and accuracy curves. We derived true positives, true negatives, false positives, and false negatives from the confusion matrix. Additionally, we can see these calculations by visually representing the formulas for accuracy, precision, recall, specificity, and F1 score in our figures. This approach ensures that our evaluation of the model's performance is both comprehensive and transparent. In the experimental setup of our study, we set the learning rate for our model to 0.01 using stochastic gradient descent to fine-tune the learning curve and minimize error margins. The model's predictions were measured against actual results using the sparse categorical cross-entropy function, while the yellow and softmax functions were crucial in handling activation across the layers of the network. We trained the model for 50 epochs, presenting it with batches of 32 images to ensure a comprehensive learning phase. This required robust computational resources which were harnessed via Google Colab's environment, boosting an 8100 GPU and 83 GB of RAM. This setup facilitates a fast and smooth training process. Python, the programming language we chose for scripting, was perfectly suited to implement the algorithms required for our AI research. In this part of our presentation, we showcase the performance of our model on the test set. Our model achieved a 99.9% accuracy rate. This is a clear indication that the model is highly successful in the task of classifying brain tumors. Now in the image you see on the screen, let me show you. We analyze the confusion matrix of our model. This matrix gives a concrete indication of how accurate our model's classification are. There is one point I would like to draw your attention to. There is only one misclassification in the matrix which proves that our model performs almost perfectly. While training and validation process or loss graphs show how stable the model's learning process is. In this in this plot, low loss values and their consistent decline over the course of the training process indicate that our model avoids common issues like overfitting. This stability is a sign that our model can also make reliable predictions against new and previously unseen data. Our results provide a powerful and promising example of how deep learning models can revolutionize the field of brain tumor classification. The outstanding accuracy rate of 99.9% achieved in our study points not only the feasibility but also to the high efficiency of using AI in medical diagnostics. This success makes a compelling case for wider adoption of deep learning based approaches in healthcare. In particular, it shows the potential to revolutionize early diagnosis and personalized treatment planning. Looking at the competitive landscape, the performance of our model stands out. Such advances are not just academic, they represent real world progress in our ability to tackle complex disease with more nuanced and sophisticated tools. The study's findings emphasize the critical role of AI models like ResNet-50 in improving brain tumors diagnosis, accuracy, and treatment outcomes. Future research should focus on enhancing AI algorithms to enable real-time tumor monitoring and personalized treatment strategies. Exploring the integration of multimodal data source and AI models can further advance the field of brain tumor classification and treatment. This study was supported by the support program of the Ministry of Industry and Technology of the Republic of Turkey. I would like to thank them for their contributions. I would also like to express my gratitude to all my colleagues and supporters who contributed to the realization of this research. Thank you.